Hi, I'm Yingkai, and today I would like to introduce you to a work I have with my colleague, Ramis Movassagh, on constructing linear distance quantum codes in the ground space of local quantum spin chains. In the first part of the talk, we introduce a new quantum coding construction where we take any classical code into a quantum code. And in the second part of the talk, we introduce a new two-local quantum spin chain and show that we can have linear distance codes that reside within the ground space of such two local spin chains. There are many frameworks that take classical codes to quantum codes, but they all share a common thread. They need some constraints for the classical codes to hold before they can take the classical codes to quantum codes. An important constraint that they need to satisfy is, for instance, for the classical codes to be linear, or additionally, for the classical codes to be self-orthogonal. In the quantum coding framework that we introduce, we do not have such restrictions. In fact, we can take any classical code to a quantum code. Our quantum code has the following structure. The logical zeros will be superpositions over code words from C0, and the logical 1 will be superpositions over code words from C1, where C0 and C1 are disjoint subsets of the classical code C. Look, notice over here that the supports of the logical 0 and the logical 1 are demanded to be disjoint. And this is an important fact because stabilizer codes do not require the logical code words to have this disjoint these disjoint code words, and hence our formalism does not generalize stabilizer codes, but however our framework does generalize all CSS codes which must have the structure. Our framework can also go beyond the stabilizer codes because while our framework doesn't encompass all stabilizer codes, it does go beyond stabilizer codes because these coefficients over here that we only demand to be non-negative don't have to necessarily have the same absolute value. They can have values that go over a spectrum. And so we like to know when our quantum codes can have a non-trivial quantum distance, namely have a minimum distance of d. Because if the minimum distance of a code is 1, it is a trivial code. It corrects no errors. We want a quantum code to be able to correct a non-trivial number of errors. And for that, we need to consider the Neel-Laflamme error correction criterion, which in matrix form can be written as this. Here, pi is the code projector and p are Pauli operators of weight at most d minus 1, where d is the number of is the minimum distance of the quantum code. In the simple case when the quantum code encodes only one logical qubit, then this code projector is given in this form. As one can see, this matrix equation is equivalent to the non-deformation conditions over here and the orthogonality conditions over here. It is easy to see that because of the orthogonal support that we demand on our quantum code construction, that if, furthermore, the classical code has a minimum distance of d, then this orthogonality condition automatically holds. And the non-deformation condition, whenever P is a non-diagonal matrix, these 0 and 1 sandwiches, they are all equals to 0 as long as P is not diagonal. And hence it suffices to consider diagonal operators P. And hence we only consider the, because of the restriction that we have on our quantum code construction, we can have these, we can just consider diagonal Paulis over here. So let's consider when this 0 sandwich is equals to the 1 sandwich. Notice that the 0 sandwich is just a linear combination of code words over here, of code word sandwiches. And similarly for the logical 1 sandwich. And hence, the 0 sandwich minus the 1 sandwich, which we want to be equals to 0, is just a linear combination of these code word sandwiches. And what this means is that we can form a big matrix that comprises where each term inside this matrix is the real part or the imaginary part of these code word sandwiches. And these code word sandwiches will encompass all information about the non-deformation conditions that we need to know. So what we are giving here is an algorithm to determine what the coefficients are, what the coefficients for our logical code words, the logical 0 and the logical 1 are from this A matrix. So first we form the A matrix, and then we find the real non-zero solution of this matrix equation AX equals to 0. Because A matrix is a real matrix by construction, any solution to this equation has to be a real vector. And whenever X is a non-zero solution, it will have some non-negative parts and you have some negative parts. The negative parts will be used to construct the logical one, and the non-negative parts will be used to construct the logical 0. And the implication of this is that we know that if we have a wide matrix, then it will have a it has a non-trivial null space. And because of that, if we and since we know what the rows and columns of this A matrix correspond to, the columns of this A matrix correspond to the code words in our classical code. Now, the rows in our A matrix correspond to the phase errors that we want to correct in our code. Well, yes, to basically the Pauli's of weight at most d-1. And hence, we know that if we have a wide matrix, that means if we have more columns than the rows, then we must be able to have a quantum code using the algorithm that we constructed, because we would have a non-trivial solution of the null space. And hence, if the number of classical code words is at least twice the volume of this Hamming ball, quinary Hamming ball of radius d-1, we can have a quantum code that encodes one logical qubit and with a minimum distance of d. Now the next question is, well, can we construct more than a logical qubit? Since this algorithm, well, it only gives tell us how to construct one logical qubit, and the answer is yes. If you look up our paper, which is available on the archive, you can see that by using a similar recursive algorithm, but this time with the additional restriction that you want to look for a non-negative solution to an equation AX equals to some non-zero vector, then you can use this non-negative solution of X to construct the additional logical code words of a quantum code in a similar fashion. So the next question is, now we have this framework for constructing quantum codes. Why do we want to put the quantum codes within the ground space of Hamiltonian? And the answer, I believe, is quite simple. If you want to store a quantum memory very robustly, you will obviously want it to have it in the ground space, because if it's in the ground space, and if you have because if it's in the ground space or in an eigenspace of the Hamiltonian, then the quantum code will not evolve according to the natural dynamics of the physical system. And this is a desirable property to have. And in fact, many quantum error correction codes have been studied. Many people have tried to construct quantum error correction codes that lie within the ground space of naturally occurring Hamiltonians. And the celebrated example is, of course, Kitaev's toric code, which approximately lies within the ground space of a honeycomb lattice with two local Heisenberg interactions. But what really motivated us was this very excellent work by Brundle et al. On quantum error correcting codes and translation invariant spin chains. And in this work, they show that if you have any translation invariant spin chain, you can have an approximate quantum error correction code with some that corrects a non-trivial number of errors that approximately lies within the ground space. However, remains the nagging question: can we have linear distance codes that lie within local translation invariant spin chains? And so, to this end, we consider this two local Hamiltonian over here, which comprises of a P term and a Q term. There are some two local interactions, and there's also some one local interactions. The overall Hamiltonian is the sum of the one local interactions and the two local interactions. The spin of the particles are integer, and hence the dimensionality of each particle is 2s plus 1, where s denotes the spin of the particle. The P and the Q terms in the Hamiltonian correspond to spin transport and spin interaction, respectively. And in particular, the P term corresponds to these local moves that swaps 0m with m0, where m is an integer from 1 to s. And similarly, Q is a spin interaction term which swaps the symbols 0, 0 and m minus m. And because using the structure of these spin transport and spin interaction terms, we prove that the ground space of our Hamiltonian is can have an exponentially large dimension. So the ground space of our Hamiltonian can be exponentially large when S is at least 2, when the spin is at least 2. And moreover, the ground space can be spanned by computational basis vectors. And these computational basis vectors are in a one-to-one correspondence with bit strings on the symbols 1, 2, 3, 4, where there are no 1, 2, or 3, 4 substrings. And hence, if one wants to construct a quantum code within the ground space of our Hamiltonian, all that one needs to do is to use our framework, our classical coding framework that takes a classical code with no forbidden substrings to our quantum code. And all that we need is this classical code to have a huge number of code words. And this is possible because our ground space has an exponentially large dimension and is spanned by product basis vectors. And because of this, we can, moreover, take any binary code into a quantum code. Namely, if you have a binary code with a linear distance, and you know a binary code comprises of strings with which have only zeros and ones. So what you can do is you can map the 0 to a 1 and the 1 to a 3. And in this way, you have a binary code on the symbols 1 and 3, and you can see that it has no forbidden substrings. And from there, you can use linear codes, you can use binary codes with linear distance to get quantum codes with linear distance within the ground space of our Hamiltonian. And this brings us to the main result of our paper, which is that linear distance quantum codes exist in the kernel of H. And in fact, we show in our paper that this fraction of correctable errors can be as high as about 4% if one uses random binary codes for this. And if one uses explicit binary codes, such as the just-the-same codes, the fraction of correctable errors can be like 3%, about 3%. And for future work, we think it'll be very nice to have explicit encoding and decoding circuits for quantum codes that are constructed using our framework, and moreover, these codes that lie within the ground space of our Hamiltonian. And it'll be interesting to see how fault-tolerant quantum computation can work on our codes that lie within the ground space of a two local Hamiltonian. Moreover, this framework that we have for developing quantum codes can be also of interest to design bespoke quantum error correction codes to enhance the performance of quantum metrology. And with that, I thank you.